When we turn over to the next page, we have what we call modified Atwood machines. And modified Atwoods are a little bit different, in one way or another. We've somehow modified them. So in this case, now I have noticed my same pulley. It's just zoomed out, but that's the same pulley and the same piece of string. So massless, frictionless, all that. And we are on a frictionless table. And we have a mass over here. Think about this in reality, even if it is frictionless, okay? If you just had a mass and you're going to drop it straight down, like let's say there was nothing attached over here to the M1. Let's say it was just a string and that was just like cut off and then you just dropped it. Think about that acceleration. Think about now if you attached it to this mass, how is that going to affect the acceleration? Isn't that going to slow it down? I mean, if this was really, really big, it would slow it down a lot, right? Now it is frictionless, but if it's smaller, it's going to slow it down a little bit less. It is frictionless. We will get into a friction example in a minute. But I just want you to think about that and how that works. So if we have a 5 kilogram mass over here, and we have a 10 kilogram mass over here. Now I know that this looks bigger than this, but we're going with what we have here. In this situation, let's stick with our system approach. That is because, just like before, the tension here is going to be the same as the tension here. Those two tensions are the same, and so they basically cancel each other out, so we're not going to be worried about them. Have the sum of our forces divided by our total mass. The sum of our forces, 98 newtons over here. Let's just make 1 is 98 newtons. We have FG2 is 49 newtons. The sum of our forces, we're only talking about what is going on in the y direction. All right, this box isn't going in the y direction at all, so we're not really going to consider that. The sum of our forces in this numerator is just going to be 98 newtons. However, the greater mass that we have over here, this is what we were talking about in the beginning, this greater mass over here, when we divide it, it is going to affect the acceleration. So if we just had 10 kilograms, we would have 9.8 meters per second squared, gravity. But we don't just have 10 kilograms, we have 15 kilograms because that's our total mass, and that's going to slow it down a little bit. A higher denominator is going to give us a smaller answer. And so when we divide these out, we get 6.53 meters per second squared. That is what we're going to have for a frictionless situation. Let's take a look at what happens if we have friction. Well, as soon as we introduce friction, it's going to slow it down even more. So that's going to have to be accounted for. And so what we have now is our sum of our forces is going to be, we have the 98 newtons, and this time it's getting slowed down because the force of friction is pulling it this way. And so it's getting slowed down. And so we have to include that because this time the friction's doing something. And so our force of friction is 0.3. Let me take a minute. Remember that the force of friction is equal to mu times the normal force. Our normal force was 5 kilograms, so that was 49 newtons, and our mu is 0.3, and that is 49 newtons. Is that friction going to slow the things down or increase their speed? Well, it's going to slow them down because it's got friction on it, and so we're going to subtract those two numbers. And so we subtract those two numbers and we divide by the total mass, which is once again 15 kilograms, and we put that in our calculator and we see what we get, and we get that the acceleration in this case is 5.55 meters per second squared. Now let's talk about, does that make sense? Well, let's compare it to the number up here. Here was 6.53, here's 5.55. The friction should slow it down, and the friction did slow it down. And so we're probably on the right track there. All right, what if we want to state the question in a different way? If we have the same diagram And we have mass 1 is 8 kilograms and mass 2 is 6 kilograms. This time we're asking what coefficient of static friction is required to keep the system from slipping. This time we're going to try to find out that mu. So we are looking for the mu of the static friction. That's what we're trying to find. All right, in this case, and I might come over here on the left and draw a little diagram. Looks something like this. Okay, they tell us that M1 is 8 kilograms and M2 is 6 kilograms. Our force of gravity is 8 times 9.8, which is 78.4. And because this is a flat table, our normal force is also 78.4. And you could say that this one's positive and this one's negative. For 6 kilograms, we multiply that by 9.8 and we get 58.8 newtons. Our formula for static friction is equal to the mu, the coefficient of static friction, times the normal force. Okay, we need to solve this for mu sub s. So the mu sub s is the frictional force divided by the normal force. So we basically are going to be looking for what's going to keep this in equilibrium. To keep it in equilibrium, we need these two sides equal to each other. If they are equal to each other, then they will be in equilibrium. So we have 78.4 newtons on one side, and we have 58.8 newtons on the other side. We need to figure in here what is the mu that we're looking for. We must need to multiply this one times the mu to get the answer over here. Let's go ahead and divide these, and so we're going to divide this by 78.4 and divide this by 78.4, and we will get our mu, our coefficient of static friction is 0.75. So what this is saying is the coefficient of static friction has to be at least 0.75 for this to stay in place. Because remember, if it's frictionless, it's going to slide off real quickly and easily. Think about those frictionless carts that we had. If you attached something to this, and this was one of those frictionless carts, it's going to go flying off. And so you have to introduce some kind of friction here. Well, how much friction do we need? We need enough friction so that it is equal to the amount of force on this side. And so that's what we set them equal to. This force going down has to be equal to the coefficient of static friction equal to this force over here. So basically what we're saying is that the frictional force, the total frictional force, has to be equal to the force of gravity on the other side. That the one hanging down has the force of gravity, the one over on the table needs some friction to stay where it is. And so this was our normal times our mu is equal to mass times gravity on the 6 kilogram side.